Okay, so I'm going to search for Visual Studio. We're going to click to download Visual Studio, download Community Edition. If you have Professional or Enterprise installed, that's fine. We're going to go here to install this. Click Continue. Okay, terrific. Now I'm going to choose the Desktop C++ environment. That's the one that you want. And then just click Install. Skip this for now. Dark, and we're going to go Visual C++. Okay, great. Visual Studio is installed. I'm actually just going to exit. Going to exit here. Going to exit here. Okay, so the next thing I want to install is VSCode. We're going to download this, and we're going to run this. And I'm going to accept this there. Okay, we're going to say install. So after Visual Studio Code is installed, started up, we're going to go to the marketplace, type in hex, H-E-X, in the marketplace. There'll be a result, hopefully near the top, that's a hex editor from Microsoft. So click install. And after that's installed, you can just close and then close VS Code. All right, for this quick overview, we're actually going to just use the same sample program that we used for the last tutorial. So that would be the SimpleMessageBox.cpp program. So I'll put a link in the description to the GitHub for that. So if you already have that installed, you're good to go. All we need is a little simple console program like this. Really, any program will do in this area, but if you want to follow along, it'll probably just be helpful if you're using the same project that I'm using. So set the project for debug build and then set it to x64 and then just perform a build. So that would be build, and you could actually just rebuild solution or build. And once it's built, you can right click here and go to open containing folder. And that's just a quick way that I use to just kind of get to the area where I need to go to see the binary. And you can see here, here's x64 and here's debug. And in the debug folder, you should have the exe and all that kind of stuff. And then after you build x64, go to x86 and do the same thing, build and rebuild solution. And after doing that, right click on the CPP, or you can actually right click on the project here and do open containing folder. Where is that here? Open folder in File Explorer. And that'll bring up the SimpleMessageBox folder here, and you can go in and verify that the debug for x64 has the exe and the PDB there. And then you can go back up here to SimpleMessageBox. If you go into the debug folder here, this is the x86 folder, and you can just verify that the exe is here and the PDB is here as well. So what this sample does isn't really that critical. The fact that it just has a little simple call to an API that it's importing is kind of the main reason why we're using this. We're going to focus on the debug x86 and debug x64. Okay, with everything built, go to the Tools menu here and go to Command Line and choose Developer PowerShell. That's going to give you a command prompt at the SimpleMessageBox root folder. And we're going to type in dir here, and we see that there's a debug, release, and x64. So we're going to go into x86 debug. And we see an x86 debug here. So you should be able to see that the link.exe is on the command line, and also there should be something called dumpbin on the command line as well. So originally, a long time ago, and this goes back several decades, there was a utility called dumpbin. Dumpbin was a standalone tool that you could use to dump characteristics of a PE executable, like the headers, the sections, things like that. It could be useful, for example, if you had an exe and you were wondering, hey, is this a 32-bit version or a 64-bit version? Because sometimes, like when you're shipping software and you ship a 32-bit version and a 64-bit version, maybe that doesn't happen as much these days. But sometimes you're wondering, well, what kind of executable is this? Is this a 32-bit? Is this a 64-bit? So dumpbin, for example, was a tool that was really convenient just to run to see kind of what the executable was. You can run dumpbin against any PE executable. So you can run it against a DLL. You can run it against an executable. And we're going to give examples of all that in here. So if I run dumpbin and I do help here, not help, yeah, sorry, wrong, I'm kind of mixing up things here. So yeah, no, it's question mark, we're here. All right, so you can see that the help for this looks very similar. In fact, it looks identical to link/dump and then help. Just remember, you can use dumpbin directly, like dumpbin question mark, or link/dump. And right now, when you do link/dump, you have the dumpbin command prompt is what I'm saying. So if you do help, you can see all the same things are, available. My voice is a little crackly, so forgive me. I don't know. It was fine all day today, and all of a sudden it's starting to get a little crackly or whatever. So if you hear a little crackly, I'm not going to bother clearing my throat constantly. So I'm just going to talk through the crackly. It should be fine. You should be able to understand what I'm saying. So I'm going to use either one or the other, dump in or link dump, or I might switch between the two. But the first one I'll do both, and but I won't do both with each command. It'll just be monotonous. You'll just get the idea. It's not a big deal. You can use one or the other for this tutorial as you walk through it with me. All right, with all that said, let's actually do something here. So we are in the SimpleMessageBox debug output directory for x86. We know that this is x86, but let's just pretend like we didn't know it's x86, right? We want to find out. Well, what we can do is we can say dump bin slash question mark, and we can see there's a lot of options here. We're going to use this one called headers. Okay, now it doesn't really stand out in the help here as maybe the first one you might want to try. And, pretty much you could probably try all. Pretty much most of these are okay to just run. I mean, there's a couple that output to file, so maybe you want to be careful what file name you choose, but most of the other ones are just reading the executable and dumping out information for you to see information about the executable. So what we're going to do is we're just going to run dump bin, and we're going to say headers, and then I'm going to say exe here for the SimpleMessageBox exe, and I'm just going to run it really quickly without pipe more, and then I'll run it with pipe more just to show you. Boom, it's going to fly by, and we can scroll up in the window here if we want to, or we can just use pipe more. Sometimes I just use pipe more like this. And we can see right up here at the top, it has machine x86. That means this is the 32-bit version. And you can see it's outputting a whole lot of stuff that's part of the PE executable header and standard. Now, you might not know about the PE executable standard, so let's just take a really quick detour here to explain this. Okay, start up a browser and type in PE executable format, and you should get a result near the top here that's learn.microsoft.com, and it's the PE format specification. So this documentation, so like if we go back to the window here where it says 14C x86, let's actually search on this page for 14C. So we'll go here and right click, and you can see it brings us down to this machine type here, i386. Now let's go find out where that's used. If we go up here, you can see that that's used in the COFF header, and it's used here in this first thing, machine, and they even have a link from here. If you click on this, it'll go down to this table here. So we'll see when we do a dump in on the x64 binary that it will be using, I think it's going to be using this one here for AMD 64. So it'll be 0x8664. Okay, so let's go back over here to the window. I'm going to maximize this. And what I want to show you is that this just has, some, information here that's coming from this header. And so what I want to do is kind of just scroll through this. We're not going to go through this in great detail, so I'm just going to hit the space bar to go through all the pipe more. So what I wanted to show you is, notice how I did dump in here. I'm going to just do link/dump/headers, and the same thing here, SimpleMessageBox.exe. Now this is going to do exactly the same thing. It's calling the same functionality. So it's basically two different physical command line utilities that can effectively access the same single utility, the dump bin utility. And if I hit enter here, you see we get the same output. So I'm just going to pick one or the other and use it, and you can do the same thing. So one thing I would like to do is I would like to take the output from this dump of the PE header, and I would like to output this to, just any old file. Let's just call this dump in headers.txt, and it's just going to output that to a text file. And in fact, actually, what I should have done here, and I'm just going to rename this file. You might want to redirect it to something where we say x86. Let's actually just open up a different command line here. So let's go here and do command line and PowerShell. Going to maximize that, and then I'm going to go into x64, and we're going to go into debug, and here's our debug. And what I'm going to do is type in dump bin /headers, and then we'll just do the same thing again, and you can see it's kind of doing the same thing. I'm going to do a pipe more on this though, and I want to show you. With pipe more, it pauses here, and you can see that that is the 8664 that I was mentioning before. So if we go over here to PE format, this utility dump in is getting this from this portion of the executables header, the COFF header. And if we go to that table, we can see this is the table here, and there's the 8664, which means that this is the 64-bit binary. Now, if you were at the command line and you had two EXEs and you didn't know which one was the 64-bit binary, this would be maybe maybe one way you could actually look to see what it is internally and look at some other things if you wanted to. So this will tell you other things about other binaries as well too. So you can experiment and maybe run against different binaries. Okay, so I'm going to hit the space bar here to go through all of that output. And what I want to do is run this again here, and I'm going to redirect to output, and I'm going to say dump bin headers. And what did we name that over here? I want to have consistency here. So I'm going to say dumpbin.headers -x64.txt and hit enter. So now we have two text files, and I'm going to start up VS Code, and I'm going to type in dot dot backslash debug SimpleMessageBox. Let's find our output. There's our output, and we're going to get the same output here. So we have both text files here on the command line for VS Code. I'm going to hit enter. That will load both of these files into VS Code, and what we can do is right click on one of them and choose to, actually I thought there was an option. I'm going to do Control-Shift-P or whatever your command, keys are to get to the command prompt for VS Code. And then I'm going to type in the word compare, and I am going to compare the active file with ... and then I'm going to choose the other file that I didn't click on. Well, no, now it's comparing. That's not what I want to do. And I'm going to say compare active file with, and why isn't the x86? That's odd, actually. It's supposed to be showing me the other file. Oh, now we get it. Okay. Well, okay. So I ran the compare command just now while I had this file active. So I'm going to choose this file. It should compare those two. And it does. You can see we have a comparison now. Now, just for some context here, the full comparison on here is probably got tons of diffs and it's not going to be tremendously useful. But when you're comparing the header and you want to see some differences in the header, even if they're the same format, like two x64 builds, for example, you're just curious at peeking at maybe some differences in there, it could be useful for that. In a pinch, if I don't have Ghidra around or something like that, and I have the build tools and I want to compare to see like maybe, which one's the x64 binary, I might run this tool. And you can see quite easily here, that this is the x64 one and that this is the x86 one. And while you're learning this, tool and maybe looking at PE, header stuff, it might be interesting to look at this. Like you can see, well, this is using the PE32 plus, structure here. And you can see some other differences here, like this portion here is using the PE32 plus, this 64-bit file. Whereas the 32-bit PE file here is using the older PE32, so it doesn't have the plus, and those are two different structures. And we'll touch on these structures in a second, coming up in a short second here. And you can see some other things here, like here's the entry point to the executable, and in both cases you can see it's the C runtime library startup code. And you can see here further down there's this 3 subsystem. If you recall from the prior video on link and the build and choosing / subsystem and console. So you can see that console flag, the / subsystem console that we specified in the prior video. And if you didn't see that video, you can just look at it. It's not critical, but there's basically a link command line parameter, which is / subsystem : and then console. And when you specify that, the linker will include in the PE header of the executable that it creates information about the subsystem you wish the executable to run under. And since these are both console applications, they both run within the console subsystem. And we can scroll down and look at some more of this, but this is just a quick little thing I wanted to show you, that you could do is compare and peruse this and whatnot. So if we move on and go back to the command line, I tell you what, we'll stick with the x64 one right now. So another thing we can type in here is we can type in dumpbin and /disassemble, and we can type in the PE executable name, and I'm going to do a pipe more on this, and yeah, I'll do a pipe more on this. And you can see you just get a little dump out here of a disassembly, and since we have symbols in the same directory, it's going to use those symbols and kind of show us a lot of good information. Now, if you ran this on an executable for which you did not have symbols, you might not get as nice of output, and we probably could actually experiment with that in a little bit, but right now I just kind of want to stay on path here. Now, you will notice that the bytes are also included here. Sometimes that actually can be helpful if you're trying to look at what machine instructions are used and you're looking at these opcodes and maybe looking at them in the manual. Really, if you have Ghidra available, Ghidra is sort of like, a better dump bin, if you will, right? So you really can get a lot of this information from Ghidra. And I probably should have prefaced that. So why would we learn a tool like this? Well, really, the world of build tools and reverse engineering, there's lots of tools and there's lots of redundancy and there's lots of overlap. And you're going to just choose the tool that you feel you need in the context. Now, having the Visual C tools available and not having Ghidra installed on the same machine is a possible scenario. You might be in a work environment that doesn't allow you to install Ghidra, but you're curious, what this executable is or something, and you wanted to look at something while you're doing some coding or something like that. So you just might run the link command with /dump or dumpbin and run it against the executable just to kind of see the PE header really quickly. I'm going to show you an example of us looking at the raw header in a second. But right now, focusing here on this disassembly, it's not like you would use this disassembly for robust reverse engineering. But in a pinch, if you kind of wanted to see what kind of machine instructions were in there, or you wanted to look at something, you could run it. It's available. So use it when you want to use it and don't use it when you don't need it, right? If you got Ghidra available and you don't mind waiting for it to start up and analyzing and all that kind of stuff, you can look at that. You're just going to get the best. You're going to get the reverse, code, the compiling, the decompiling, and all that kind of stuff. So a tool like this is something that you use fast and quick on the command line. You're just checking something in the PE header really quickly, or you're curious, where the location of a function is, or you're curious, how was this function compiled? What is the machine? What does the assembly look like? You just want to peek at it really quickly. Maybe you have symbols available. It's just convenient to run it really quickly. Now let me show you something you can do. You can actually do this. You can actually take this disassemble command, and rather than do pipe more, by the way, I hit Control C there. And so now that I'm broken out from that prior command, I'm actually, and you know what, let me actually maximize this. Sorry, I didn't do that earlier. So I'm going to make this a little bit kind of bigger. And I'm going to type in dumpbin, and I'm going to just output here. And you can just output to dumpbin.asm, for example. And that's just going to create a file there. And I'm going to say VSCode, simple thing. And we're going to go to the asm file that we just output. And it will load this in, and we can actually just look around here. So if I want to try to see if I can find main, is main in here somewhere? Main. And we could find main. There's main right here. Main right here. This is actually a little stub that jumps to main. So let's just keep searching, see if we can find main. Let's see if we can find it as a whole word. There we go. Here's main. Let's see if we recognize this. Oh yeah, here we go. Here's our little prologue code here. This is written in C. Of course, it's not our prologue code. It's generated by the compiler. And it looks like we have some setup here. And then look, here's our call to message box A. And since we knew the function had a call to message box A, we actually probably could have found main just by typing in message box A, and I'll turn off casing here in VS Code. And then you can see there's not really that many hits to message box A. So if you just search around, you can actually find main. Let's go back to the command line. I type in clear here, and so let's type in dumpbin / let's try exports and the exe. So exports are things that the exe itself is making available to the outside world. Now, typically it's DLLs that are doing that, but an executable can have an export, and this one doesn't have one, so we're going to see nothing there, but I just wanted to show you this really quickly. So if I go ahead and run dumpbin exports on this, we can see it, outputs a summary of the various sections which are in the executable, but nothing else is output. Here, let's type in exports, dumpbin exports, and :Windows \Explorer, and let's hit enter on that. And you can actually see that Explorer actually does have an export here, G-tray triage block. It's just something in the PE executable that's exported for other applications to use. So now let's type in dumpbin /imports, and let's run that against our SimpleMessageBox executable. Now, imports are sort of the opposite of exports. Imports are the shared library code that our executable wants from the outside world when it runs. So most executables do have imports because they need support from the runtime libraries or the operating system and a whole lot of other stuff. So generally, most executables will have a whole bunch of imports. And our SimpleMessageBox is no different. Let's do a pipe more on that and hit enter. And you can kind of see here, this is showing you the PE COFF, COFF PE dumper, and it's showing you the tables, and it's showing you various things like, for example, from VC runtime, 140D, it wants these imports. So these are functions that are implemented in this DLL, and our executable is asking for these. Now, we did not ask for these specifically. In fact, let's not pass this up really quickly. This is user 32, and you can see our executable is asking for MessageBox A from user 32. It's asking for it because we have a call to it in main. So it's because of our code that this user 32 exists here. If our code didn't make a call to MessageBox A and there were no other references to user 32, we would not even see this whole entry here. Okay, so if we go back down here to VC runtime 140, we can see our executable is importing a whole lot of stuff from this DLL. But this is not stuff that we are importing explicitly within the logic of our code. This stuff is imported implicitly by the C runtime library. So our application is a console application, and Visual Studio sets up the project for us, and it compiles and links it for us. And as part of that entire process, it creates our executable with a dependency on the runtime library and, one or more OS DLLs as well. So if we statically linked with the runtime library or any other library, we wouldn't actually see imports, because statically linking means that you include something within the executable, so there's no need to import at runtime. One reason why you might link statically to some, library is that you want your executable to be self-contained and not be reliant on a shared module. Another reason is you might not want it to be reliant on the outside world. You might not want to expose the fact that you have an import. Not that that's super high security and prevents somebody from picking apart your executable in Ghidra, but it makes it more challenging. If your executable is pulling something in via an import, it's quite obvious and straightforward, like, hey, you're bringing in this code, and people can look at the imports that an executable pulls in and maybe make some educated guesses on how it works. Or sometimes you might be curious, how does this executable, do XYZ? Well, sometimes if you dump the imports that the executable requests, via imports from the operating system or whatever DLLs that it's requesting imports from, but especially I would say the OS, because sometimes an executable might be using certain APIs, and you'll learn about the APIs it's using by looking at the imports that the executable requests. And I say request here, but what I mean is, when you link the executable and it creates these tables within the executable, within the PE format, these tables being things that define what the executable imports, in a sense, it is a request. It's sort of like you would say a deferred request, and it happens anytime that the executable gets loaded into memory. These requests get resolved by the loader. The loader will go and find the libraries that satisfy the requests for these various imports. We touched on this some in the prior video on WinDBG and Shadow Store and the link compile and workflow and whatnot. And if you go look at that, you can see more about imports there. So moving on here, we can see that there's other runtime library stuff that's being imported. I'm going to hit spacebar. We see there's some stuff from the OS. Kernel 32 is most likely always going to be there. And then we can see actually it's finished now here. It's at the bottom. These are actually summary of sections. We talked a little bit about sections in the prior video. The text section is one of the code segments, for example. So here we have the data section, and that's going to include global and static variables. And our data is going to contain read-only data. So that'll be things like string constants and whatnot. Resources. Text is code, and text BSS is like uninitialized global data and variables. And you can actually read, you can actually just like go online. Most of these, you'll find information on them and whatnot. So I'm going to run exports, dump bin exports again on our executable, just to show that there are no exports. And what I want to do is I want to actually go and run this against user 32. Type in Windows system 32. User 32. And when you type that in and you hit enter, you're going to see a whole flood of exports. Now remember, user 32 is where we get MessageBox A. So watch this. We can actually do a pipe and a select string and type in MessageBox and then close. And you can see it found a whole bunch of MessageBox functions. It has MessageBox A, which is the ANSI version, and MessageBox W, which is the wide character version. So we can see that user32 has a boatload of exports. That's because it's a library that's providing a lot of OS functionality effectively to any applications that need that, including operating system, applications. All right, so now I want to type in dumpbin, and I want to type in a symbols command, and I want to type this against the object file. So the object file, as you know, the compiler generates the object file, and then the linker takes one or more object files and links it along with any library code that it gets pulled in, and it takes all those and combines them together to create the executable. It actually takes bits and pieces from all of those to create the final executable, so not everything in the object file ends up in the executable. That probably just goes to say, but wanted to mention it. So if you have several object files and you're curious about the symbols in relation to a particular object file, or maybe several object files, and you're looking for something, you can actually dump the symbols for an object file by using dumpbin symbols and the object file. So let's do that here. And you can see a lot of information was output here. Now, if I go up here, we'll do a pipe more. I just kind of wanted to show you could dump symbols that are both used and exported, quote unquote exported. We don't say exported in the sense of an object file, but in a sense, you can kind of think of it like that. For example, with this object file, we could actually do a select string and look for main. And you can see here that it has main external right here. That's because the linkage is external as opposed to static. Now, if I actually output this, we could actually go and say obj output, and let's just do this. Let's actually say obj dumpbin symbols.text, and let's code sim.text, and it'll bring us into VSCode. So I'm going to type in main, and you can actually see here that there's main. It has external linkage, meaning it didn't have static main, which means that when we compiled it, we effectively took the compiler default, which is not to specify linkage, which means the function has external linkage. And all that means is that it can be called from something outside of the object module. In this case, we really want it to have external linkage because the link will fail if it doesn't. And the reason why is that the C runtime library has a dependency on needing to find main somewhere within the user-created object modules, which means the object modules created from the source code that we have created. If you don't have a main function, you get an error. Just try it. Try to take main out or rename main. In fact, we could do it really quickly here. Let's jump over the compiler. Let's call this main underscore not main. Okay. And I'm going to build, and you'll see that, it says it must return a value. It's not letting me get away without a value being returned. I'm going to return 0. You can see here we get unresolved external underscore main. And it's telling you here the runtime library is not able to, get everything it needs. So this is to kind of highlight the interplay at compile time and link time. At compile time, a bunch of object modules are created. At link time, those object modules are looked at by the linker, and the linker can use those to create a bunch of, resolutions to relationships. So in a traditional console application, you have a main function that needs to be there because the runtime library has a function that's calling main. Now, it just so happens that the build tools, when they set up a project, they link by default to all the right runtime libraries and everything. So usually you don't have that issue. If anything, you as the user may forget to create a main, and you'll get a warning or you'll get an error about that at link time, as we just saw here. So let's actually restore our program back. Let's build it. Great. And let's go back. And rebuilding is important just to make sure we have an executable there in case we run more dumpbin commands. So when we come back here, we see that this is the main function. It has external linkage, which means that we didn't do anything within our module where main exists to prevent main from being exposed to the outside world, meaning other object modules by default can use main. Because by default, functions in C++ have external linkage, which means it's okay for other objects, object modules to require and call into our object modules functions. in this case main. Now, if you add the static keyword before a function, you're basically telling the compiler that you want it to have internal linkage. Let's not go too into that right now at this point. Okay, so you can see that our function main has external linkage, and you can see that it is in SECTA, sect A. And if you look, there's a sect A up here, which indicates that that's in the .text section, which is the code section. Interestingly, like if we search for our title bar message string thing, right? So here's this one here. This is the actual symbol for that constant, the message box title. And you can see that that's in SECT, sect 12. And you can see up here that sect 12 is in the RData or read-only data section. So this output is not used all the time by most folks, but it can be useful to peer into an object module to see what symbols it's using or creating and that kind of thing. And so I thought it was worth just maybe giving you a quick overview on it. All right, let's go back to the command line, and I want to type in dumpbin disassemble and the obj again. So let's type in the obj and then just hit enter. And you can see it dumps out a disassembly. Now, if we scroll up here and we look for main, so here's main right here. And in main, you can actually recognize the code. Here's our call to message box right here. So here's the parameter setup. You can see it's zeroing ECX, and it's loading RDX with the hello world string, and it's loading the R8 with the title string. And it's zeroing R90, which I believe is MBOK. And again, you may not really need this if you have Ghidra available, of course, right? But if you needed to get a quick disassembly of an object module or something like that, you could run this. Now, I don't believe this if you just have the release build. So even if you have symbols for release build, it will not give you a disassembly. So we could actually run that here. Yeah. It doesn't give it to you for that. So back here in the debug folder with where the debug.exe is, so type in link/dump, or you can use dumpbin and headers and our executable, and I'm just going to do a pipe more on this. So here we have our header, our header stuff, and actually I'm just going to scroll down to the bottom here, and then I can just scroll up with my mouse wheel. Okay, so remember it has x64 and all that jazz. So what I want to do is I want to now type in code for VSCode, and I want to run this on the executable. So we're going to load this executable into VSCode. VSCode is going to give us a little warning, and we click the open button and we choose the hex editor, so it opens up to the hex editor. And what we're going to do is we're going to look at the raw dump here in relation to the dumpbin output, in relation to some of the structures that we have access to, and let's go. Okay, with a browser running, type in PE executable format again, and this time go to the Wikipedia article. So if you go to the Wikipedia article here, you can actually see, so you can see this 5A 4D, that's a 16-bit word, and the 4D is the low order byte, and it occurs first in memory. That's because this is little endian, the Intel architecture in Windows, so it's going to be in little endian. And if we go over here, you can actually see it's 4D in the low order word, and then 5A in the high order word. So we have M and Z. Now, if you go back over to the browser here and you type in MZ header, you can actually read more about this if you want to, and some of the history behind it. That's actually this person's initials here, Mark. And you can actually read more about this guy and the history of, this signature and whatnot. Now, this is not really used by Windows applications, but at the time there was this migration from DOS to Windows. There was a need to make it so that if you ran a Windows program from the DOS command line, you would get some kind of message to tell you that you shouldn't be doing that. And so essentially the stub that's up front here will actually emit a message to say, oh, this is meant to be run as a Windows application. It's not really meant to be used at the DOS command line. the idea was, let's create these new Windows executables that will run under Windows just fine, but if the user tries to run them from the DOS command line, they'll get this little message that will, be user-friendly rather than the whole thing locking up or something like that. Now, when looking at this Wikipedia article, I notice, like it has these machine instructions here where it's loading the 16-bit AX register with the data segment, and then it's loading that into the DS register. Now, this was very common in DOS assembly language, because in DOS assembly language, you would pretty much be managing the data segments and the code, like what your segments were, like the ES register and the DS register. When you're working in these flat models like x64, all those segments are set up for you, and you don't have to set any of that stuff up. But in the old days, you might load the AX register with the value for the data segment, and then take that value and then actually load it in the data segment. And you might wonder, why don't they just do move DS, at data? Well, the reason why they don't do that is you have to move, you could only set segments from other registers. You couldn't set segments directly from memory or from a constant value or something like that. So if you needed to get a constant value loaded, or you needed to get something from memory, you would put it in a register, and then you would take that register and then move it to the segment. So this is kind of silly, but when I saw these machine instructions, I have not seen like 16-bit registers used in a long time. And so just looking at this Wikipedia article just sort of brought back these memories, and it was just, I don't know. And now you guys might be saying like, okay, well, that doesn't mean much to us. And I totally get it. But one day you guys are going to be older, and you're going to look at some code that they don't, some style of code or something, who knows how things are going to evolve. It's going to evolve a lot in your era. It's going to evolve quite a bit. And you guys are going to look back on some old stuff, and you're going to be saying like, wow, remember we used to do that, and that kind of thing. Now, if some of you are, kind of, remembering that time and you're a part of that time, hey, no problem, whatever. But I think some people out there are, are maybe, they didn't play around with DOS. So, I mentioned in that spirit. Okay, so let's get back to that raw header here in VS Code. So in VS Code, here's the raw header. Let's try to walk this through a little bit. We see we have this MZ right here. One thing I wanted to do here is let's go back to the browser and let's type in PE executable format. Let's go down here to the Microsoft PE format page. And then let's scroll down here a little bit and look for the MS-DOS executable header. This is the one that has MZ. Now you'll notice here there's not a lot of detailed documentation here. So it's like it has this, but it doesn't detail things about it. Now let's go back to the Wikipedia page. If we go to the Wikipedia page, you can see it shows the signature, and then it has this, pointer to PE header here. What I want to do is jump over to Visual Studio, where our SimpleMessageBox program is. Then do Control, Shift, and F to bring up Find and Replace Files. We're going to do Find in Files. And then type in image DOS header. And then from this drop down, choose Visual C++ Include Directories and hit Find All. And you're going to see a hit for that in win.nt.h. So double click on that to open it up. And you can see here is the image DOS header. Now, the magic number, this is going to be the MZ 4D, the 5A4D. And let's look at these really quickly here. So we have bytes on last page, pages in file, relocations, and then there's size of header in paragraphs. So notice that this is the first word. So there's one word, 2, 3, 4, and the fifth word is this E_CPAR header, which is like, paragraphs in header. So let's actually look at that. So it's 1, 2, 3, 4, 5. So a word is 16 bits or 2 bytes each. Let's go back over to the raw dump. And in the raw dump, you can see that there is 1 word, 2 words, 3 words, 4 words, and 5 words. So these two right here are the number of words, 0004, because remember, it's little endian. So the low byte comes first, and the higher bytes come thereafter. So this is 16 bits. There's only one higher byte. And so this would be a high byte of 00. So effectively the number is 04 paragraphs. Now a paragraph is 16 bytes. In fact, each one of these lines is 16 bytes. And it's not uncommon to see a dump of data where each line has 16 bytes or some multiple of 8 bytes. Not that it has to be, but it's very common to see that. One of the things to note about that is 16 bytes is a paragraph. So each one of these lines is a paragraph or 16 bytes. So we know that this header has 4 paragraphs. So that would be 1, 2, 3, and 4. Okay, so let's go back over to the structure here. Now you notice that the last long in this structure is a thing that is LFA new, and it's documented as the file address of the new exe header. Now remember, this goes back to the days when you had DOS was the primary operating system and Windows was the newer one. And the Windows EXE was something that was going to be a close relative to the DOS EXE, but it couldn't be identical. And one of the things they really try to focus on with these things is how do you make things backward compatible? How do you make it so that, a user that accidentally runs a Windows EXE doesn't crash the machine or something crazy like that? And that goes back to the stub that I was talking about where it emits that message. In fact, if we go back over to this dump, you can actually see the messages right here. This program cannot be run in DOS mode. This is like a little DOS program that's going to execute if you run this from a DOS environment. The last thing in this structure is a long, which is 32 bits. This 32 bits is a quote-unquote file address of the new exe header. So the old exe header is this DOS header. The new exe header is the portable executable. So what we're going to do is we're going to look at this value in the raw dump and see if we can't eyeball the new header. So let's go back over here. And we know that there are 4 paragraphs in this DOS header. So there's 1, 2, 3, and 4. And we notice here are the 32 bits which represent that value LFA new. In fact, let's just for the heck of it grab this structure, let's copy it and bring it over here to Notepad or to VS Code and put it over here on a pane over here to the side. Let's grab these bytes. I don't know if this will let me copy these bytes. And let's just pop these bytes here at the end of this comment. Well, it doesn't seem to like that. Okay, it has a copy thing here, so I don't know why it's being painful. Okay, what we're going to do is we are going to, we need to, let's bring this down here to the bottom. Okay, thank you. Okay, no, I don't want to do anything, thanks. Okay, so, so let's put here 0x F8, 0x 00. In fact, we don't need to put the 0x. This is hex. So F8, 000000. Now, this is little endian, right? So little endian, what that means is as a 32-bit value, this is 000000 F8. So it's F8. Now we could actually go to the programmer calculator right here in Windows and we could type in like F8 and see that it's 248, but we actually don't need to do that. We actually are happy that it's in hex. We don't really need to know its decimal value. So this is an address in the file, which means it's really an offset within this file, starting from the start of the file. So starting from 0. So if we want to find F8 from the start of the file, you just go to the F line and go to the 8 column right here, and there's 5045. And you can see that 5045 is P and E, which is part of the PE signature. So we see 50450000. So let's go over to the PE format documentation and let's search for, you know what? I'm going to try searching for 5045. See if that's in there. Okay, let's actually go over to Visual Studio here, and I'm going to pin the WinNT header since we tend to be focused on that. And we're going to search in this header for 4550. So let's search for 4550. And sure enough, here's the image NT signature. So if I grab this signature and I go over to the documentation and I search for this in here, is this in here? Okay, let's look for the header where this appears. So here it's showing that there's the MS-DOS stub, and then it's followed by the signature, which is PE00. That's what we're looking at now. And what we did is we went over to the source code here to find actually the pound defined in the WinNT header that is used. Like if you're going to write a program that's going to look for this header, you would use this pound defined, for example. So going back over here to the documentation, we can see that this COFF header follows that signature. So let's check that right now. So we're going to go back over to the raw dump, and we're going to see that here is the PE header, right? It's 50450000. And then immediately following that, notice that, again, this is a little endian, so it's 8664. So if we go back over here to the documentation and we search for 8664, you can see that is the indicator for a 64-bit file. And you can see this is in the machine type section that we were looking at earlier. If I scroll up, this is the header that we were just looking at, right? So it's really this field here is what we're looking at. And we see that this field right here, that's where it is in the raw. And we go over here and we can see that this is the value that that field has right now at this time. So this is kind of to triangulate between several things. One is the documentation here, right? The other one is looking at this raw header, right? Another one is looking at the dump bin output, and maybe it's not triangulation, maybe it's quadrillation, whatever, quad something, because I'm going to mention the structures in code. And in a sense, dump bin is probably using these same structures that are here in the WinNTH file. So for example, if we look for the machine type here, let's see if we can find that in here. So if I find machine, you can see here I found this, and here's image file header, and here's machine, and in here they call it COFF file header. So this is the COFF file header here. It's machine, number of sections is the next one, time of date, pointer to symbol table. So you can kind of see the programmatic stuff from the SDK and the headers, some utilities that are written using those headers, dump bin, link, and whatnot. And then we see the raw binary dump here in VSCode in the hex editor. And then we see the relationship to the documentation. So the documentation can be helpful to point out certain things, but it might not point out everything that you can take advantage of in the programmatic, quote unquote, I'm using that loosely, that term, in the headers that help you write software, right? In the headers of the SDK. Sometimes if you're going to try to write some code and you're going to use you want to write things properly and use defines where they're available, or use existing structures if they're available. It's always usually good to do that if there's an SDK available, because then, if that changes, a lot of these structures wouldn't change, not these older ones. If your app is built using an SDK, it's usually good to use those defines rather than just create your own. So if you want to write a program like that in the correct way, you might want to, use the right structures, and you might have to go and look in the header file. Maybe not everything's going to be spelled out in the documentation. This is not uncommon with various things when it gets to be lower level, and you want to really go and look at the source code or the header files, maybe to find out some details or to fill in the blanks. Okay, actually, and let me go back here. So you notice there's this image file header. So I'm going to actually search for image NT header, and you can see there's signature here, and this signature would be the PE00 header. Okay, so that signature would correspond to this signature here. And then you can see following that signature is image file header, which we were already looking at. And if I'm in Visual Studio, I can just highlight that and hit F12. It'll take me there. And this is what we were just looking at, machine, sections, etc., etc. So I'm going to hit Control- in Visual Studio to go back. And then they have some other stuff here, and and so on and so on. All right, everybody, that's it for this video. Just a brief overview of the dump bin and link dump, as well as a segue sort of into the PE executable. And I thought it would be a nice segue from that other video because we did touch on imports and linking and building, and so this kind of talks about dump bin, and that was sort of a way to get into the PE header and sort of look at all that. Now there are a lot of tools that load PE images. Ghidra is an example of one. It'll load it in and give you all kinds of information and decompile stuff and whatnot. So you're really kind of set there. By the way, you can do that with an OBJ with Ghidra as well. You can take an OBJ. In fact, if you want to experiment, load like the OBJ from this sample program into Ghidra, and just like with an EXE, it'll prompt you. It'll ask you if you want to analyze and all that stuff, and it'll it'll decompile main and show you stuff about that. You're not going to have to use this tool all the time, but you might be using the tools in a situation where Ghidra is not around and you just want to do a quick peek at the PE executable header for some reason. Maybe you're just wondering, is this a 32-bit executable or is this 64? Or maybe you don't even have any of the tool, but you have VS Code available. You might just be able to load up the header, and since you may be working with a lot of EXEs, and if you're working with a lot of Windows EXEs, you might remember some fundamentals of the header, so you can just peek in there, look at the PE header. You find that PE header, then you look a couple over and you can see the bytes for the indicator. Right away you can tell if that's a 64 or 32-bit binary, and things like that can be helpful. All right, everybody, that's it for this video. If you like this video, I hope you'll click like, and if you want to subscribe, of course, I'm going to be super happy if you do. All right, everybody, that's it. Be well, be safe, and wishing you well, and until the next video, take care. All right, see you later. Thanks. Bye.